Dnaiel Wagner from DE-CIX. Daniel's going to talk about quantum key distribution at IXPs as part of the QNet Q project.
That's right.
Over to you.
Thank you very much. Tervetuloa, hyvää päivää. That's all I can say here. Kiitos. It's my pleasure to be here again. I was given my first talk 3 years ago in 2022 here at nog.fi meeting. You might remember me from back then. It was a humorous talk about how to not do networking. Today, and also sort of as a sponsor, I try to keep the advertisement slot in the beginning super brief, just not to bog you too much with that. I'm talking about the quantum key distribution project that we at DE-CIX are currently involved in. Yeah, you might wonder what are these networking guys doing. DE-CIX IXP, Internet Exchange Point, we love peering. I hope you do too. And if you do not, then please come see me. And we are, to the best of my knowledge, the first and the only so far Internet Exchange Point in the world that has a dedicated research department. And I'm super happy to be part of that. I joined that about 5.5 years ago. And yeah, we're looking into the hot stuff. So that is quantum key distribution for this talk today. So what's that thing at all? You might have noticed that there is a quantum hype somewhere out there in the world. And in our case, we are investigating what we can do with that in the context of IXPs and data centers. So first off, a bit of the technical stuff, because I'd like to share this with you. Instead of using the traditional way to transmit information through a optic fiber, we, in the case of quantum communication, use some magic cryptographic protocols. In that case, it's BB84, to entangle photons, and the entanglement itself, there are 4 different cases. The entanglement itself conveys the information. So that means if there is a photon source and there is a photon sink, and if they are synchronized together, they can exchange information via the entanglement of photons. And yeah, this allows you, because reasons, to exchange information where you know that in case if there is an eavesdropping on the communication, you will see that the photon entanglement is sort of broken because of timing problems, and then afterwards you know that something happened to your communication channel. So that makes it specifically secure, and this is why sort of it's getting really interesting for most of some of the industry branches, and also for governmental and some institutions, and they try to just be on the top notch of this new technology to not miss any chances or not get hacked by some magic new communication channels. So what we do is basically we exchange information that only the sender and the receiver can actually decode to exchange some secret key, and the key is used to then in the end encrypt the original payload. So data rates here are fairly low so far, couple of kilobits if I'm not mistaken, and if you want to have like 400 gig communication encrypted with that, the photon entanglement will not do the job, but what you could do instead is just exchange the key via this quantum channel and then encrypt the payload on a different channel. So why is this now super secure? Well, I'm not a physicist, and here's the proof. In short, it sort of has something to do with timing, and you would need to know what you are going to read in order to copy the photon entanglement in the moment it is supposed to be sent already. So that sort of needs you to somehow foresee the future and know what you will have to copy before you could even read it. The moment you read it, the entanglement is broken, and then afterwards the receiver will know that there is something happening along the path. Okay, so as I said, what is it not? It is not the encryption itself, it's just the key exchange. So you will not go ahead and use these BB84 technology to encrypt a couple of hundred of gigs. That's not what's going to happen. And it also does not solve the problem of authentication. So still, you will need to have to trust that the other side is actually the one you want to talk to. So if there is another device, let's say on the other end, and somebody just replugs the cable, you will see an interruption, and most certainly there's an alarm going off anyways. But in case somebody would actually sneak on your channel and could be the other one, or whoever is now on the other end of your channel, there's just no authentication. You will not realize that there is somebody else there. So you still need to trust between all of these two parties. Well, this is sort of for granted if you're in the same data center or if it's your testbed at home, but still for the widespread technology deployment, one would need to check that again. Okay, so now what is hot? What do we do? Actually, lots of governmental bodies, they do give away lots of funding money. They say, hey, we do not want to miss this cool opportunity. We need experts. We need some guys with experience from the industry and also from the academia side. So we get funded by the state to look into such technologies. And as you can see here, DE-CIX is also on there, and we've got lots of other universities and some other partners from national research institutions, Fraunhofer here, all German-based. However, the funding is sort of from the European side and as well as from German federal institutions. And yeah, they have the physicists, guys, and they are the physicists, and we do networking. So that's how the things come together here a bit into play. And this overall has sort of the goal to just deploy this new technology for photon entanglement. It's just what I said. And especially what we are doing is we try to integrate these kind of network devices into our existing infrastructure, and especially in the context of IXPs. So that's what we're doing here. We have a number of different scenarios that we're going to look into. The details on the next slide. This is the map of Germany. We've got 4 test beds, whereas the first one is in Berlin only. Then they have this long distance track which connects Berlin to Frankfurt. This is where we at DE-CIX are. And then there is a third, the third one is in Munich, and the 4th test bed, and they look into different use cases and different scenarios. Start off with the first one, which is in Berlin. The partners there, what they are doing is they are trying to find side channel attacks. Spoiler, there was a paper, I think 2 years back, published already by some Swedes, and they said traditional side channel attacks work very well on QKD devices, and that was sort of a bummer, I want to be honest. And they are investigating if for our use cases inside the project there are also side channel attacks that are actually feasible. Let's see what the results are. This is an ongoing project. There are no results published yet, but after that, you can read it up. Then, this is a very honest slide, to be honest. The racks are empty. We have our test beds deployed, or we will have them deployed in Frankfurt in multiple locations. These are just placeholder numbers, so usually in the end, it's going to be at least one co-located with one of our edge sites, and then some satellite sites that will be covered by QKD device deployments. So first off, last week I gave the same talk, and I could not say that there's anything inside the rack. As of today, there's an update. The devices are on the way. They were sent from the colleagues in Berlin that were tweaking the devices and adjusting all of these magic physicist stuff. And now they send it to Erfurt, which is somewhere here in the halfway along the path. So hopefully by next week we'll have the devices there finally to actually evaluate all the things that we are looking into details next few slides. Then along the path, that is the so-called 3rd test bed, that is a long distance link. And what is usual for links is that optical communication cannot reach like 1,000 kilometers without any repeaters or something alike. And same is true for the QKD devices. So what you could see here, these purple boxes along the path, I have a more detailed map. And after that, this is just a schematic. There are so-called repeaters, where there is an incoming signal, and it's remodulated and then transferred to the next hop, let's say. The distance usually done by these kind of hops is 80 kilometers. So every 80 kilometers, you will have one of these repeater devices. And just to start an honest discussion, the problem that I think is there, where it's not encrypted. So wherever you place your repeaters, you will have to take care that this is an actually trusted and secured environment. Otherwise, this whole thing is sort of a joke. And then, last but not least, we've got the 4th test bed from the colleague partners at Fraunhofer and Hochschule Nordhausen. They are looking into some medical use cases. They've got a health kiosk somewhere in a clinic 220 kilometers apart from each other, and they're looking into use cases there. So here's a detailed map of the long distance link. This is sort of the flagship test bed from the whole project, because that is like the thing where the German funding body says we want to have a quantum network. A network usually for them, of course, means there should be links. And I say as a IXP employee, I say that there should also be nodes. This is why we have DE-CIX down here. But what they always use for advertising this whole project is the long distance link. Spoiler again, that is delayed in deployment, let's be honest. Yeah, so what you can see is like every say 80 something, like 70 something kilometers, there's one of these repeaters along the path, and it's sort of tricky to get a secured environment along somewhere in Germany along Autobahn. Actually, they deployed next to one of the motor highways. So, as I said, we are a research department. The question is, what do we actually look into? And first of all, we never had QKD devices at an IXP, so we will look into all of these most trivial things, the ones that pop up first, where to put that. Yeah, of course, what is the rack space requirement? What is the power consumption of these devices? I can give you already some numbers. Rack space, well, that's easy. You can basically fit all of this stuff into one rack, depending on what you want to do. And the peak and average power consumption is about 1 kilowatt. Depends on the devices once again, but it's like not 20 kilowatts or something like that, so it's actually sort of doable. Yeah, with the temperature and vibration, we're checking into that once it's deployed. Let's see. Then the question next up is, how do we connect these devices? Well, I think the answer here is, once again, pretty simple. It's all single mode. You just need a single mode connection for one communication channel, of course. Then the question is, once again, in the metropolitan area, maybe some things are different than from long distance links. What is going to be a distance requirement here? What are the error rates? What bandwidth can be reached? And what's the latency? And is that of any problem? Then we were looking into what could be the use cases. I want to be clear that this is not part of the QNetQ project currently, but once it is deployed, one could think of actually going into more use case orientated questions like, can we secure the BGP on the platform? For example, can we have our routers use the QKD channels to exchange BGP quantum encrypted BGP messages? And then, and this is sort of what the wishes are, we always have to look into the future, is how about the data plane traffic? We still got like, at DE-CIX we've got like about 17 terabits in peak traffic to maybe encrypt if you wish. If you want, we will be looking into that. And then the next thing is, how about we, instead of providing, let's say, a route server where customers pick up routes or prefixes, we put a QKD device and customers can pick up QKD information, the keys there. We start exchanging keys to our peers so they can use it. So we become something like a QKD service provider. And instead of having a route server, you then have like a quantum key server or something like that. Other different use cases. We might want to look into that. But first of all, we need to investigate about like the physical infrastructure, what are the requirements here and there. As I said, number of limitations apply. The hardware is, let's say, research close, it's bleeding edge. It's not that cheap yet, but we're looking into that. Currently, things are very costly, but fortunately there's funding money, so we can actually get those things. Then sometimes some of the cryogenic cooling was a problem in the beginning. Turns out it's not that bad. And in the end, what is the goal of the research, but we're not looking into like producing these things ourselves, but still is what we can communicate back to the outside, is to say, okay, we want to have this whole technology at best in a pluggable transceiver. That would be a dream. Well then, as I said, there's also some things to look into with regard to the distance and the end-to-end security. The question is about signal loss. How well is that covered when looking at IXPs, when you're already in the data center? And yeah, as I said, there is a bandwidth requirement of about 100 kilometers for the long distance link, so there's also limitation here and there. Then the key material itself is just there, but you don't know which parties are actually exchanging it, so the operator must be trustful. And as I said, every hop sort of is a weak spot, in my opinion. And yeah, we are of course, we wish to have higher ranges. So more like that. As I said, there's no authentication in the technology. So is Bob really Bob and is Alice really Alice? Nobody can tell us. So this is what we have to rely on, where we have to rely on traditional channels. That is just, I don't know, the TLS authentication or something like that, the existing technologies, just to make sure that the party on the other side is the one I really want to exchange my key with. And then, last but not least, there is still PQC, the post-quantum cryptography. This is sort of like an orthogonal approach. And as we can see, there were some contests hosted by NIST, for example. NIST, huge US-based security institute. And they were saying, okay, we want to have the best, whoever can give us the best PQC algorithm, we're going to reward you for that. But nobody, at least from their side, was looking into quantum key exchange. Quantum key distribution, QKD. So where's the contest for QKD? That's a question. And here it says it's sort of a rivalry. I tend to disagree with that. I did not do the slides. I tend to disagree with that. In my opinion, they can be used alongside with each other. Once they both are developed at a certain point, you use QKD to exchange the key material and then use that key material for whatever your PQC algorithms are going to look like. So yeah, that's what we're basically looking into in this project. Some concluding words I just leave here up on the slide, and with that I'd like to conclude my talk. Maybe open a sort of round of discussion, and if not, we can have a chat later on. Thank you very much.
Thank you, Daniel. Do we have any questions? Easy questions are fine.
There's one.
When you talked about the key exchange and said that it's not an encryption.
Yeah, not itself. Yeah.
And it's not. You can't know if the other end is who.
Yeah, who they really are.
Yeah.
No authentication, and it's not an encryption itself. Yes.
Yeah. So how is it better than the current?
Well, yeah, that's a good question. So if I can't know if the other side is the one I really want to talk to, and it's just the exchange of the key itself and the traffic, the payload traffic itself is not encrypted by the quantum channel, why are we looking into that? That's sort of a good question. The thing is that we want to look into that and get those two factors ruled out. We want to fix that. We want to find ways how to overcome these hurdles. Until then, it's just research, but we want to be the ones that are looking into it first, just to know that if there's any chance to do something cool with that, we have already experience with that and already have the hardware. So yes, at the current state, it is research. It is like, let's say, not developed to some sort of industry standard. That's why it's not around. But once it might reach that level, it could be the one that takes up. Yeah, that's why it's not industry standard, because it's just not really what you wish for. We've got lots of things to look into. That's right, research. Early stage. Anytime.
Any more questions?
So who's got quantum hardware at home? Oh, that's a lie. All right. With that, I think then we're done.
Thank you very much, Daniel.
Anytime. Thank you.